In this video, we're going to be talking about the photoelectric effect. Photoelectric effect is a property where light hits a piece of metal, and then off of that metal, electrons are removed, and they leave it with some given velocity, called v. Everything that we have seen thus far still is going to hold true. The energy of the photon is still going to be equal to h times f. This is always going to come back into play, and pretty much, like I said, you're always going to be using this in modern physics problems. And again, h is Planck's constant. It's 6.63 times 10 to the negative 34th joule seconds, which leaves us with energy in joules, which is good. That's what we're used to, and we're okay with that for now. Later we'll see another unit of energy that's going to start coming into play. So here is a look at what the photoelectric effect kind of looks like. So you have light coming into a tube. In this case, it's an evacuated phototube. Evacuated means that there's no air in there, so there's nothing to stop the photons from coming in. And you've got a metal plate here. This metal plate gets hit, and these photoelectrons get removed from the plate. Photoelectron just means that it was an electron that was emitted from the plate because of a photon. Now you see that you've got a metal plate on this side, a metal plate on this side, and electrons going from one side to the other. So when you have that, what do you think is going to be created? A current. And you measure a current with an ammeter. Now you're going to get a positive side over here. You have a negative side over here, and that's because you're having the negative move from left or from right to left, so this side has to be positive in order to attract the electrons. That's the basic setup here. So now what are some of the things that we can look for? Well, we could look for a voltage that is created by these electrons. We could look for the current created by the electrons. And we're not really ever going to be looking at a resistance of the electrons. Now, you see down here, there's a battery hooked up. So one of two things can happen here. You can either imply a voltage to the circuit and stop those electrons, or you can allow those electrons to move through and a current will go and it could charge the battery. Now this is similar to, but not exactly the way solar cells work. There's a lot more involved with a solar cell than just straight photoelectric effect, but it is the precursor to solar cell technology where it's charging a battery. Now this setup here, it would most likely be used, you're going to be changing this voltage to find something related to the photon. So let's take a bit closer look at the photoelectric effect here. So what do we have? We got a piece of metal. On that piece of metal are loose electrons kind of hanging out. They're like just, sitting there. You know how metal works. It likes to move electrons around. Now, if something with energy comes in, it hits one of these electrons. These electrons can move off in some given direction. Now, what has to be true about the energy of this electron? Okay, well, based on conservation of energy, you should say that the energy of the electron should be equal to the energy of the photon. It's not. Now, here's the reason. The energy of the photon gets used up by the metal. The metal has some given amount of energy that it takes just to tear the electron away. That we call the work function of the metal. Work function is often written as W sub naught. Then to that, you add the kinetic energy of the electron, and that will give you the total energy of the photon. Now, we said the energy of a photon is what? H times F. So H times F should be equal to the kinetic energy of the electron plus the work function. Oh, I just flip-flop those, don't worry about it. Or you could say the kinetic energy of the electron is equal to HF minus the work function of the metal. The work function is completely dependent on what the metal is. On the AP test, you'll either be asked to find it, or you'll be given it in the problem. So depending on which is trying to be, there's no chart that you can look these up on the AP test. There are many charts out there that you can find them outside of the test, but you won't have access to them. So they'll either give you the information, or they'll ask you to find what the work function is and give you the other things. So, given this, and you can't see me pointing at it, given this equation and our work function, I'm going to slide this over. So, the kinetic energy of the kinetic energy of the electron is equal to HF minus the work function. Now, what happens if this electron is stripped off but not allowed to move anywhere, so it has zero kinetic energy? So if the kinetic energy is zero, then HF minus the work function is equal to zero, so HF is equal to the work function. This is a special F now. That we're going to call F naught, where F naught is the frequency to remove an electron. So F naught is the minimum frequency needed to remove the electron from the metal. Now again, because your work function is going to be different for different metals, the frequency, F naught, will be different for different metals. However, for the same metal, that frequency will always be the same. If you were to look in a graph here of this, where you have the kinetic energy of the electron on this side, and on this side you have the frequency of light, you would see a graph that looks something like this. So here, this would be F naught to give you zero kinetic energy. Now you could go through, and once you know what F naught is, you can go back and figure out what type of metal it is. A lot of times in labs what you'll have is you'll be mapping these kinetic energies of given electrons based off of the voltage that you record, or the current you record in the circuit, and then you can extrapolate that back to find the F naught, the initial frequency that you would need, which then will let you find the type of metal. So now let's try a problem based off of photoelectric effect. So the work function for a silver surface is 4.73 electron volts. Find the minimum frequency that the light must have to eject the electrons. So we are looking for the minimum frequency, or F naught. So for F naught, we know kinetic energy must be equal to zero, because we started this, that the energy of the photon is equal to the kinetic energy plus the work function. So the energy of the photon, or HF, is now going to be equal to KE plus naught, the work function. KE is 0. So H times F naught is equal to 4.73 electron volts. Alright, we have not talked about the electron volt in a while. We did talk about it very quickly during circuits. It's the amount of energy that one electron has when you put it through 1 volt of potential difference. So 1 electron volt is equal to 1.6 times 10 to the negative 19th joules of energy. H, we saw, was 6.63 times 10 to the negative 34th joule seconds. There is, however, another form of this Planck's constant. Now I have lost that number. So let's go backwards and let's do it the other way then. Instead of converting Planck's constant into electron volts, let's convert this electron volts here into joules. So if 1 electron volt is 1.6 times 10 to the negative 19 volts, joules, sorry. Multiply this by 1.6 times 10 to the negative 19th joules to give yourself an energy in joules. So Planck's constant, 6.63 times 10 to the negative 34th joule seconds, multiplied by your minimum frequency, is going to be equal to, when you multiply that out, the number gives you 7.57 times 10 to the negative 19th joules. So now we divide by the Planck's constant, and you get F naught, or the minimum frequency needed, should be 1.14 times 10 to the 15th hertz. Hertz is still our unit for frequency, just like it was before. A couple of quick tips. Whenever you have an energy in joules dealing with photoelectric effect, it should be on the order of 10 to the negative 19th. So 10 to the negative 20th, 18th, 17th, those are all fine. Whenever you have a frequency for photoelectric effect, it should be on the order of 10 to the 15th hertz. So 14th through 16th is acceptable. You could get higher, you can't go much lower. This is the minimum frequency for silver. So you can't get any lower than this for silver and still have electrons removed. Work functions are relatively constant. Some metals have larger work function, means it takes a more energetic photon. Some have a bit lower, but very few of them get super low. So that is the basics of the photoelectric effect. It is kind of the precursor into solar cell technology, but again, there's a lot more involved in the solar cells. And it is one example of how waves act as a particle. Whenever you see H in your problems, or anywhere, this is light acting as a quantized piece of energy. So it is a particle.